In the 11th standard, we have seen certain physical quantities such as displacement, velocity, and acceleration. And we have seen the kinematical equations based on this. That are the terms related to translational motion. There are some terms which are related to these terms that are the analogous terms in rotational motion that we have also seen, that is angular displacement, angular velocity, and angular acceleration. And we have seen that in case of translational motion, force F is equal to ma, that you know. And in case of rotational motion, torque 2 is equal to I into alpha. That is, force produces the translational motion and torque that produces the rotational motion. That is, we have seen linear acceleration, A analogous to angular acceleration, force analogous to torque. Here, we need a replacement of a term which is analogous to mass. Here, as we know, the expression for force F is equal to ma, expression for linear momentum P is equal to mv, expression for kinetic energy, that is linear kinetic energy, will be 1/2 mv square. These equations, that is force, momentum, and kinetic energy, these equations, there is one of the common term, that is mass. Therefore, we have to need the replacement of a term, that is mass. Here, we know that when you open the door, we know that door rotates about its hinges. At that time, we have given a certain angular displacement in order to open the door, and for that the effort has been made at that time. That depends not only upon the mass of the door but also depends upon the perpendicular distance from the axis of rotation, and that perpendicular distance is called as moment arm. That is, here, as the distance from the axis of rotation increases, the small force will be applied. And if the distance from axis of rotation is small, then the large force will be applied. And that's why you know that the handles of the doors that are at a large distance from the axis of rotation, that is from the hinges. Here, in this case, we have seen that in order to replace the term, that is instead of mass, that term depends not only upon the mass but also depends upon the perpendicular distance from the axis of rotation. And that actual term we are going to see now, that with the help of expression for rotational kinetic energy in expression for rotational kinetic energy, which is a sum of translational kinetic energies of all the particles. From that expression, we are going to say here, that is the term moment of inertia. Here, at the expression for rotational kinetic energy, if we consider a rigid body, if this is a rigid body, this rigid body rotates about an axis. The axis of rotation passes through the center. You know that this is the axis of rotation. This axis of rotation is perpendicular to the plane of the figure. The axis of rotation passes through the center and perpendicular to its plane. Now, this rigid body rotates with a constant angular velocity omega about an axis passing through its center and perpendicular to its plane. What is meant by rigid body? We have seen that a body whose particles always maintain the same position with respect to one another, whether or not the forces are acting on that body. That body is called as rigid body. And what is meant by axis of rotation? That also we have seen. When rigid body rotates, then different particles of the body revolves in circle. Centers of all these circles are situated along a straight line, and that straight line is called as axis of rotation. That axis of rotation we have seen. Here we have considered the body, rigid body rotating about an axis passing through its center and perpendicular to its plane. It rotates with constant angular velocity omega. If we can say that that object or the body, it is to be made up of n number of particles having masses m1, m2, mn. Their perpendicular distances from the axis of rotation are r1, r2, rn from the axis of rotation. Here, suppose this is a particle having mass m1. Its perpendicular distance from the axis of rotation is r1. This is a particle having mass m2. Its perpendicular distance from the axis of rotation is r2. Here, this is a particle having mass mn. Its perpendicular distance from the axis of rotation is rn. In this way, when the rigid body rotates with a performs uniform motion at that time, all the particles that performs the circular motion. with a constant angular velocity, but their linear speeds are different because the radii of different circles are different, or they are situated at different distances from the axis of rotation, and therefore though they move with a constant angular velocity, though the body moves with constant angular velocity omega, the linear velocities of all the particles are different because their radii are different. Therefore, linear velocities of such particles are, that expression for linear velocity is equal to radius into angular velocity. Therefore, V1 is equal to R1 omega, V2 is equal to R2 omega. In this way, velocity of n number of particles is Vn is equal to Rn omega. These are the linear velocities of the particles. Now here, with the help of these linear velocities, we can find the translational kinetic energy of individual particles. And then sum of all this translational kinetic energy of individual particles give the rotational kinetic energy. Therefore, the translational kinetic energy of first particle having mass m1, which is at a perpendicular distance r1 from the axis of rotation, then its kinetic energy will be 1/2 m1 v1 square. That means it will be 1/2 m1 r1 v is equal to r omega. That means r1 square omega square. This is the kinetic energy of first particle. Then kinetic energy of second particle, you can say it will be 1/2 m2 r2 square omega square. In this way, we can find the kinetic energies of all the particles. Then kinetic energy of nth particle, it will be equal to 1/2 mn Rn square omega square. And sum of kinetic energies, translational kinetic energies of all these particles gives the rotational kinetic energy, and therefore the expression for a rotational kinetic energy will be equal to sum of the sum of translational kinetic energies of all the particles, and that will be equal to 1/2 m1 r1 square omega square plus 1/2 m2 r2 square omega square plus 1/2 mn plus dot dot dot. That will be plus dot 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 1/2 mn Rn square omega square. Now see here, if we in this expression kinetic energy, rotational kinetic energy, here it will be equal to 1/2 m1 r1 square, 1/2 common cut way happen, 1/2 m1 r1 square plus m2 r2 square plus dot 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 plus mn Rn square omega square also common. That means 1/2 omega square common. This you can write rotational kinetic energy is equal to 1/2. This term in the bracket that indicates summation integral I goes from 1 to n. That is sum of product of mass of each particle and square of its distance from the axis of rotation. That is summation integral ranges from 1 to n, because we have considered n number of particles, and that will be equal to 1/2 summation I goes from 1 to n mi Ri square omega square. And this term, that is summation I goes from 1 to n mi Ri square is equal to I, and therefore rotational kinetic energy is equal to 1/2 I omega square. This is an expression for rotational kinetic energy, which will be equal to 1/2 I omega square. Here we have seen this term I, that is called as the rotational inertia. That is the rotational inertia, or it is also called as the moment of inertia of the object or the body about an axis of rotation. And therefore, we have replaced the term, that is moment of inertia, that is I is equal to summation I goes from 1 to n, I goes from 1 to n mi Ri square. That is replacement of I to mass and replacement of omega to v. That is there we have replaced moment of inertia to mass and angular velocity to linear velocity, and therefore this term I is called as the rotational inertia. It is also called as moment of inertia of a body about an axis of rotation. Here in this way we have seen what is this moment of inertia. Then what is the definition of this moment of inertia? Here question can be asked, derive an expression for rotational kinetic energy. At that time you have to prove that rotational kinetic energy is equal to 1/2 I omega square. Here this I is equal to, that is moment of inertia I is equal to summation I goes from 1 to n mi/ri square. What is its definition? Sometimes question can be asked like this: define moment of inertia, its unit and state its units and dimensions. What is its definition? Moment of inertia of a body about an axis of rotation is defined as sum of product of mass of each particle and square of its perpendicular distance from the axis of rotation. That is the definition of moment of inertia. That is mi/ri square. Sum of product of mass of each particle and square of its perpendicular distance from the axis of rotation. Here, this equation is only for finite number of particles. But if homogeneous rigid body, or you can say that there is no discrete particle, or in another words you can say that there is a continuous distribution of particles, then at that time instead of this summation we have to replace integration, and therefore in such a case moment of inertia can be obtained by using this formula I is equal to integral r square dm, where you can say that dm is a mass of very small particle and r is distance from the axis of rotation. In such a case, the moment of inertia can be obtained by using this formula I is equal to integral r square dm, where there is a continuous distribution of mass. Then at that time you can use this formula. Here this formula is used in various cases, that is I is equal to integral r square dm. Now on what factors the moment of inertia of the body depends, that we have to see. Here, the moment of inertia of a body depends upon mass, shape and size of the body. Mass, shape and size of the body. Number 2, it depends upon distribution of mass about the axis of rotation. And number 3, it depends upon position and orientation of axis of rotation. So here, you have to remember this, on what factors the moment of inertia of the body depends. Moment of inertia of a body depends upon mass, shape and size of the body. It depends upon the distribution of mass about the axis of rotation, and it also depends upon position and orientation of axis of rotation. That is, if position of axis of rotation changes, distribution of mass about the axis of rotation goes on changing automatically. Its moment of inertia also goes on changing. This is related to moment of inertia. That is, you have to remember the definition, unit and dimensions of moment of inertia, expression for rotational kinetic energy, that is E is equal to 1/2 I omega square, and you have to remember that on these 3 factors the moment of inertia of the body depends. Now we are going to find out first the moment of inertia of a ring first here. What do you mean by ring? Suppose this is the ring. This is the ring. Here, an object is said to be ring when the mass is situated uniformly on the circumference of a circle. Then that is called as a ring. Here we have considered a ring. The axis of rotation of this ring passes through its center and perpendicular to its plane. Here the ring rotates about this axis of rotation. We want to find the moment of inertia of such a ring here. For that purpose here, I have said that an object is said to be a ring when mass is uniformly situated on the circumference of a circle. Here, this is the 2-dimensional object having a very negligible thickness. We have considered a ring having mass m, whose perpendicular distance, see here, this is the perpendicular distance from the axis of rotation here, and it will be equal to r. M be the mass of ring, whose mass is situated at a distance r from the axis of rotation, which is the radius of this ring. Then moment of inertia of thin uniform ring is equal to product of mass and square of its distance from the axis of rotation, that will be equal to I is equal to mr square, because its mass m is uniformly situated on the circumference of a circle with a distance equal to a radius r of the circle. Therefore r be the distance from axis of rotation, which is same, and m be the mass of that ring. Then moment of inertia of a ring will be equal to I is equal to mr square. Here you have to remember this equation, I is equal to mr square. Now we want to find out an expression for moment of inertia of disk, mi of disk. On this topic, question can be asked. You have to derive an expression for moment of inertia of disk. Here, with the help of this diagram, I can explain that. This is the disk. We have considered a ring out of that. This is a ring whose thickness is dr. Its distance from axis of rotation is smaller. Here it is a ring whose radius is capital R. See here, this is a two-dimensional object. You can say that when we say that a disk is to be uniform, that means its sigma is equal to mass per unit area, that is surface energy. You can say it will be equal to density, that is sigma, that is mass per unit area, that will remain constant throughout. Disk is said to be uniform when its mass per unit area, that is surface density, you can say it will be, that is mass per unit area, remains constant throughout. Then you can say that the disk is said to be uniform. Here, if we consider a uniform disk having mass m, a radius r, rotating about an axis, that axis of rotation passes through its center and perpendicular to its plane. When you say that this disk is to be uniform, at that time the disk is to be made up of number of thin concentric rings whose radius ranges from 0 to r. Out of that, we have considered one ring whose thickness is dr and which is at a distance r from the axis of rotation. At that time, we want to find the moment of inertia of a small ring, and then if we integrate that equation, then we can find the moment of inertia of disk, because that disk is to be made up of number of thin concentric rings. For that purpose, first we want to find the moment of inertia of one such a ring. And for that purpose, as you guys say that sigma is equal to mass per unit area, that means sigma is equal to m upon pi r square. This is related to disk. But if we have considered a small ring whose thickness is dr, which is at a distance r from the axis of rotation, then in such a case, the area of a ring is equal to circumference into thickness or the width. And you know that circumference will be equal to 2 pi r and thickness will be equal to dr. This is the area of a ring. Area of a ring is equal to 2 pi r dr. Then its sigma is equal to, you can say it will be equal to dm, because dm be the mass of that ring, and that will be equal to dm upon area will be 2 pi r dr. Therefore, mass of that ring will be equal to dm is equal to 2 pi sigma r dr. This is the mass of a ring. Dm is equal to 2 pi sigma r dr. Here, sigma is equal to m upon pi r square, that is related to disk. Then area of ring is equal to circumference into thickness. Circumference of that ring is equal to 2 pi r into dr. Then sigma is equal to dm upon 2 pi r dr. That is dm is equal to 2 pi sigma r dr. This is the mass of that ring. Then we want to find the moment of inertia of a ring first. That is IR is equal to chota r, small r, I can write here. IR is equal to integration of r square dm, because r means its distance from axis of rotation, where dm be the mass of that ring. We want to substitute value of dm here. Then IR is equal to, you can write it will be equal to r square dm, that is 2 pi sigma r dr. This is dm into r square. If we integrate this equation, then we can find here, first this is the moment of inertia of this small ring. Then if we take in this case, if we have taken the integration of this, at that time the ring having a radius thin constant, I have said that a uniform disk is to be made up of number of thin circular concentric rings whose radius ranges from 0 to r. Then we want to find the moment of inertia of disk. ID is equal to integral limit ranges from 0 to r 2 pi r dr r square. That will be equal to, that means it will be equal to 2 pi r 2 pi sigma r dr r square. Limit ranges from 0 to r. Then here moment of inertia of disk, you can see it will be equal to 2 pi, here 2 pi sigma constant, that is out of integration 0 to r cube dr r square r, that means r cube dr. Limit ranges from 0 to r. Then ID is equal to 2 pi sigma, you know that integration of r cube dr will be equal to r raised to 4 upon 4, therefore, and lower limit is 0, upper limit is r, therefore we have to substitute upper limit minus lower limit. Then I can write it will be r raised to 4 upon 4 minus 0. And therefore ID, that is the moment of inertia of disk, ID is equal to 2 pi sigma I can write here, sigma will be equal to mass upon pi r square, that is m upon pi r square into r raised to 4 upon 4. Therefore, we can write this as pi gets cancelled. This will be 1/2 mr square, that is mr square by 2. That is moment of inertia of disk, ID is equal to 1/2 mr square, or you can say it will be equal to mr square upon 2. This is the moment of inertia of disk rotating about an axis, passing through its center and perpendicular to its plane. Here question can be asked, you have to obtain or you have to derive an expression for moment of inertia of disk. First, when you obtain the moment of inertia of a ring, and from that you can find the moment of inertia of disk. Here, that is the expression for, in order to solve the problem you have to remember also, that is how moment of inertia of thin uniform disk will be equal to mr square by 2. Here we are going to see now, up to this we have seen what is meant by moment of inertia, concept of moment of inertia from expression for rotational kinetic energy. Then we have seen on what definition of moment of inertia, on what factors the moment of inertia of a body depends. We have seen the moment of inertia of a ring. You have also seen the moment of inertia of disk. Now one point we are going to see now here, the radius of gyration. This is also important. Radius of gyration. What is this radius of gyration? See here. With the help of this figure, I can explain that. Radius of gyration, that nothing but the distribution of mass about the axis of rotation. That term related to the distance from axis of rotation. Here, as we know that the moment of inertia will be equal to I is equal to summation I goes from 1 to n mi square. Here in this diagrams here, this is a mass m. Here we have replaced whole mass of the body as a point mass, that is m. that point mass m is at a distance k from the axis of rotation. Here, this m is replaced by whole mass of the body. You have to remember whose moment of inertia is same as that of the body. That means moment of inertia of a body, that body is treated as a point mass m whose moment of inertia is same. Here, the m is at a distance k from the axis of rotation, and therefore its moment of inertia is same throughout. That means I is same. Therefore, as you know that the formula for moment of inertia, you can write it will be equal to, from this I is equal to product of mass and square of its distance from the axis of rotation. That will be equal to I is equal to mk square, where k is the radius of gyration. That is k is equal to under root of I upon m. As I have said that k is a measure of length. Therefore, its unit is centimeter. Or SI unit is meter and CGS unit is centimeter. Here, as it is a measure of length. And from that you can find its dimensions. That is L raised to 1, M raised to 0, T raised to 0. What is the definition of this radius of gyration? See here. Radius of gyration of a body about an axis of rotation is defined as distance from the, here you can say that radius of gyration is defined as the distance between axis of rotation and a point at which whole mass of the body can be supposed to be concentrated so as to possess the same moment of inertia as that of the body. That is called as radius of gyration. See again the definition of radius of gyration. Radius of gyration of a body is defined as distance between axis of rotation, this is the axis of rotation, and a point at which the whole mass of the body can be supposed to be concentrated so as to possess the same moment of inertia as that of the body. That is called as radius of gyration. And therefore we have written moment of inertia I is equal to mass into square of its distance from the axis of rotation. I is equal to mk square, where k is the radius of gyration, and that will be equal to under root of I upon m, where I be the moment of inertia of that body. Then what is the application of this radius of gyration? As we have seen that radius of gyration is a measure of length. That means as the axis of rotation changes, the distribution of mass about the axis of rotation goes on changing. Automatically, its distance from the axis of rotation goes on changing. Here, if you can say that small value of k indicates that, suppose here this is the small value of k. This indicates that the particle is close to the axis of rotation. And large value of k indicates that particles are widely distributed from the axis of rotation. Here, a small value of k indicates that particles are very close to the axis of rotation. Automatically, its moment of inertia is same. Here, large value of k indicates that particles are widely distributed from the axis of rotation. Automatically, you can say that its moment of inertia is also large. That means this k, when k is small, its moment of inertia is small, and when k is large, its moment of inertia is also large. This is related to radius of gyration. See here, on this topic also a question can be asked. Define radius of gyration. Yeah, and its formula is very important in order to find out different radius of gyration of different bodies. That is, if you know the moment of inertia of that bodies, then you can find the radius of gyration of that body. You have to remember that radius of gyration is a measure of length. It depends upon distribution of mass about the axis of rotation. And small value of k, the particle is distributed close to the axis of rotation. That is, it is close, having small moment of inertia. Large value of k, that means the particles are widely distributed from the axis of rotation, having large moment of inertia. All these are related to radius of gyration. You have to remember its definition, its application also, and its formula. Then in the next session, we are going to see the expression for perpendicular axis and parallel axis. This is the end of this session. In the next session, we have to see all this related to principle of parallel axis and principle of perpendicular axis.